Good morning everyone. My name is Vidisha Joshi. My class is BSc PCM third year regular. My roll number is 225045 and my topic for presentation is dual space, contravariant tensor, covariant tensor and mixed tensor. Let us first understand what is a vector space. Let V be a given set. We should call elements of V as vectors. Let F be a field whose elements will be called scalars. We say that Vf is a vector space if following conditions are satisfied. The first condition states that there exists an internal binary operation plus on V called vector addition such that V plus is an abelian group. Now, to be an abelian group, it should satisfy the axiom of associative law, commutative law, existence of identity and existence of inverse. The second condition states that there exists an external binary operation called scalar multiplication such that lambda belonging to F and alpha belonging to V. This implies that lambda into alpha belongs to V. The scalar multiplication satisfies the axioms that are for every alpha comma beta belonging to V, lambda belonging to F, we can say lambda bracket alpha plus beta is equals to lambda alpha plus lambda beta. Second, for every alpha belonging to V, we can write bracket lambda plus mu into alpha is equals to lambda alpha plus mu alpha. And third, bracket lambda mu into alpha is equals to lambda bracket mu alpha. And 1 dot alpha is equals to alpha. 1 is unity element of the field F. Now theorem, let Vf be a vector space, then 0 into alpha is equals to 0 for every alpha belonging to V. Here 0 is additive identity in F. Minus 1 into alpha is equals to minus alpha. Minus alpha is inverse of alpha in V. Alpha into 0, lambda into 0 is equals to 0, 0 being the 0 vector. Lambda into A is equals to 0 implies that either lambda is 0 or alpha is 0. Now basis of vector space. Let Vf be a vector space, a set S that is lambda alpha 1, alpha 2 to alpha n of vectors of V is called the basis for V if the set is linearly independent, that is lambda 1 alpha 1 plus lambda 2 alpha 2 plus 2 lambda n alpha n is equals to 0. This implies that lambda 1 is equals to 0, lambda 2 is equals to 0 to lambda n is equals to 0, where lambda 1, lambda 2 to lambda n all belongs to F. Second, for each alpha belonging to V, alpha can be expressed as linear combination of vectors of S. We say that S spans V. Now what is a dual space? Let us take a vector V. The dual space of V denoted by V star is the set of all the linear functionals of V. Linear functionals are functions that takes a vector as input and gives a real number as output in a linear way. Now for vector addition we can see U plus V into A is equals to UA plus VA for every U comma V belonging to V star and for every A belonging to V. For scalar multiplication we have alpha U into A is equals to alpha U bracket A for all alpha belonging to F and for all A belonging to V. This vector space is called the dual space of V. Tensors. Now first let us see what are tensors. Tensors of various orders are functions from product set of vector spaces into the set of real numbers. Tensors of different orders are element of vector spaces formed by repeated tensor products of MM and M star M. Now a contravariant tensor. An element of MM into MM or MM square is called a contravariant tensor of second order or second rank. If T of ij where I is equals to 1, 2, 3 to any value n and j is 1, 2, 3 to any value n are component of a vector belonging to mm into mm with respect to basis ei, and t of I dash j dash are component of same vector with respect to basis ei dash are related by law t I dash j dash is equals to p I dash I p j dash j t I j. This is known as law of transformation of contravariant tensor of order 2. An element of mm into mm to r copies or mm to the power r is a contravariant tensor of rank r. Now what is a covariant tensor? Elements of m star m into m star m are called covariant tensor of rank 2. If t of ij, where I is equals to 1, 2, 3 to n and j is equals to 1, 2, 3 to n are component of a vector belonging to m star m into m star m with respect to basis ei, and t I dash j dash are the corresponding component of same vector with respect to basis ei dash, then they are related by a law t I dash comma j dash is equals to p I dash p j dash t I j. This is called law of transformation of covariant tensor of order 2 or tensor of type 0, 2. Elements of mm star into mm star into mm star s copies or m star m to the power s are covariant tensors of rank s. Now what is a mixed tensor? mm into mm r copies into m star m into m star m s copies or mm into r into m star ms are called mixed vectors of type r, s. If t I1 I2 to IR, J1 J2 to JS are components of vector belonging to MR into MM star with respect to basis EI, and T I1 dash I2 dash I to I dash R, J dash 1 J dash 2 to J dash S are corresponding vector components of same vector with respect to basis EI dash and are related by a law t I1 dash I2 dash to IR dash J1 dash J2 dash to JS dash is equals to p I1 dash to p I2 dash p I dash R upon I1 I2 IR p j dash J1 J1 dash p J2 J2 dash to p JS J dash S t I1 I2 to IR and J1 J2 to JR. Now mixed tensor of type 1 1. If t I j are component of a vector which belongs to mm into m star m with respect to basis ei, and t I dash j dash are corresponding component of same vector with respect to basis ei dash, are related by the law t I dash j dash is equals to p I dash I p j dash t I j. It is the law of transformation of tensor of type 1 1, and t I j are component of mixed tensor of type 1, 1. Now let us take an example. Show that Kronecker delta is a tensor of type 1, 1. Relative to basis ei for mm, components del ij of Kronecker delta are given by del ij is equals to ei ej. For another basis ei dash of mm, del of I dash j dash is equals to e of I dash and e of j dash is equals to p I dash I ei bracket p j dash ej is equals to p I dash p j dash ej, or del I dash j dash is equals to p I dash I p j dash del ij. But the above is the law of transformation of a mixed tensor of type 1 1. So we can say that del ij, that is Kronecker delta, is a 1 1 type tensor. Thank you.